So this is an exciting class today because today we're getting into what is the heart and soul of statics, which is everything in equilibrium. This is really what this whole class has been building up to, and what the rest of the class is going to be about is everything that we've talked about, all of these vectors, what it looks like when they're in equilibrium. And what we mean by that is that the forces, the sum of all of the forces acting on, in this case, we're discussing a particle. All of the sum of the forces acting on a particle are equal to 0. And so there are really kind of two applications of this, right? We know from Newton's second law that F equals ma. And so if our force is 0, our mass can't be 0. We don't have objects with no mass. This means that our acceleration must be 0. So when we're talking about things in equilibrium, we're talking about things that are either at rest or they could be moving, but they're moving at constant velocity. So we're taking a look at these basic cases of where we don't want things to move, which may sound like an ideal scenario, but as engineers, there are a lot of times when we don't want things to be moving. Bridges, for instance, are a great example of a time when we don't want things to be moving. We want it to kind of stay where it is. There may be some flexibility in that. And as you get on into further classes, like strength of materials and things like that, you learn how to deal with objects bending and material deformation, material deforming. But for us in statics, we're really just looking at things at rest or with constant velocity where all of the forces acting on it add up to 0. And so the way we often see that is like, for example, you might see, a book. A book is sitting on a table here, right? Everything is at rest, nothing is moving, and we say that the forces on the book are in equilibrium, where here the forces on the book are the weight of the book, right, is acting down on the table, and the table is pushing back up on the book, right? So this is just how we had talked about it at the very, very beginning of class, right? These forces that we're seeing on these objects. We're going to start describing them in ways that are helpful to us to solve problems. So the main way we do that is with something called a free body diagram. Let me move this out of the way. Whoops. So we work a lot with something called a free body diagram. You may also see this shorthand as FBD. You'll see it written like that in this course a lot, and maybe even going forward. And this is when we're taking something like that book sitting on the table that we had over here, and we're removing the actual object that we're talking about from it so that we can represent it as a point, see all of the forces acting on it. So before we said we had this book, we had this on a table, so it has the normal force from the table acting on it, and also the force from the weight of the book itself, right? So if we were to draw that as a free body diagram, all that means is that we're representing the book as a single point, as a particle. The particle within the book, right, is experiencing the weight of the book, the force of the weight of the book, acting down on it due to gravity. We could also call this mg if you wanted to. Mass of the book times gravity is how we could find what the weight is. And then we have that normal force coming up from the table. So this is a basic free body diagram, just a single point with all of the forces labeled on it. Now, often our systems are a little more complicated than just a book sitting on a table, so you might have something like the image shown, where you have multiple points you could pick from to make free body diagrams. So, for example, if I look at point E, the point where this little weight is sitting within this little V and has a rope coming off of it. If we look at the free body diagram for that point E, I'm looking at point E here, or the ball itself. I'm looking at the ball itself, I'm representing it as just a point. So what that ball is experiencing is, of course, it has the weight of itself, right? The weight of itself pulling down. It also has the force of cable CE holding it up, right? There is tension in that rope. There is force being pulled through that rope that is holding up the ball in this chain through the pulley and the spring and attachments to the wall. There is force in that cable. I'm going to call it FCE, representing the cable between C and E. And then there's also the normal forces from the V that it sits within. So everywhere that it touches, perpendicular to where that ball is touching, right? So it was perpendicular when we had a book sitting on a flat table. Perpendicular was just straight up. Now we're at this 30-degree slant. So our perpendicular to that 30-degree slant is going to be this 30-degree offset. Normal forces, normal force, that is experiencing from sitting on the wedges there, right? So this angle here is the 30 degrees. So this would be another example of a free body diagram for the ball itself. We could also pick other points within this system to look at a free body diagram for. So for example, if I look at point C, I might draw a free body diagram for point C where I have the force FCE is now pointing down, right? It's pulling it down. Before it was pulling up, and now we're seeing the opposite, equal and opposite reaction, right? Equal and opposite reaction. We're seeing the force being pulled down from point C. So before we were going to point C, now it's from point C. And then we also have, to the right here, the force from the spring. I'm going to call it force CD, just because it points from C to D. But it's the force going through that spring that's holding up this system here. And then at this 60-degree angle, if I were to label it like this, 60-degree angle, we have force from B to C. I'm going to call it force BC. So this is the free body diagram at point C. These are all of the forces that point C is experiencing. It experiences a force from every cable that touches it. Everything that is interacting with that point causing a force is what we're seeing here. Now in this case, we're imagining that the ropes don't actually weigh anything, so there's no weight component here, right? There's no actual object. We're looking at a single point. But if it were an actual object, just as we did with the ball, then we would account for the weight. In general, when you're drawing these free body diagrams, your forces point away from the object. So notice I didn't draw these normal forces pointing in to my dot. That would be a no-go. Whoops. Well, that's not a good color for that. That would be a no-go. We don't draw them pointing in towards the point. We always draw them pointing away from the point. And this is just so we can keep our positives and negatives straight. It's a lot easier to see when you're working in the positive X direction and the positive Y direction if you're always facing out from the point. So let's bring together everything we've talked about so far, and we're going to bring it into these solving equilibrium problems. Everything we've talked about in force vectors, these free body diagrams, all of these things will work together. We're going to use them to solve problems in equilibrium. And there are 4 main steps when we're solving problems in equilibrium. The first one is that we're going to want to set a coordinate system. It will usually be the XYZ coordinate system, but not always. Sometimes it may be beneficial to reorient or turn or skew your system, but most of the time we're going to be working with our XYZ coordinate system. Today we're only going to talk about 2D, and we'll get into some 3D ones next week in the next video. The first thing is set our equilibrium system, or set our coordinate system for equilibrium problems. X, Y, and Z, which way do those axes lie? Then we're going to draw a free body diagram. We always want to draw a free body diagram. Anytime we're solving these problems in equilibrium, always draw a free body diagram. This step is critical. It is very, very difficult to solve these problems if you don't set up these diagrams, because it can be really hard to see where things are pointing, and it also helps you know if you're missing any forces, right? So sometimes you may not immediately see the force, you may not think about the weight of something, or you may forget a normal force or a friction force, and if you have them all in your free body diagram, it's a lot easier to see if you missed something and what it might have been. So we always want to draw a free body diagram to start these problems. Then we'll set up our equilibrium equations. So we're going to set up our equilibrium equations, and those are that the sum of our forces is 0, right? The sum of our forces is 0, meaning that our resultant force is 0. Or more importantly, the way we look at it in this class is the sum of the forces in the x direction equals 0, and the sum of forces in the y direction equals 0. And I write it out like this for a reason. This is actually extremely important that we note these as two separate equations, because in this, we're going to be solving systems of equations where we generally have two or maybe more unknowns that we're trying to solve for. So we're taking it back all the way to maybe Algebra 2, where you learn, maybe even algebra, where you learned to solve these systems of equations, and we're going to do that using these summations, which is our last step. Our last step is just to solve. And sometimes you have to apply these equations multiple times to multiple different points within a system to find what you're looking for. This will make a little more sense as we work through some problems, and we're going to work through multiple problems today. This is going to be a longer video. It's going to feel like a lot, but it's really, really important to get this concept down. This is probably the single most important concept that we've been building to and will build off of from this point in the class. So let's look at an example problem. The first one is going to be a really simple example just to see that we're getting the idea. So the first example we're going to look at is just the setting up and solving. We're already given a free body diagram. Here we're going to be finding the magnitudes of F2 and F3. It gives us the free body diagram. We don't have to draw it. We know it's a free body diagram because there's no object in it. All it is some forces around one single point, which is the center point here. So all we'll be doing is applying the equilibrium equations and seeing how that works. So our two equilibrium equations again are that the sum of all the forces in the x direction is 0, and the sum of all the forces in the y direction is 0. So the way that I write that out is I need to find all of my components of each force and add them together and set them equal to 0. It does mean that we're going to have our unknowns within those equations, right? We're going to have F2 and F3 just marked as F2 and F3. We don't know what they are. We're going to have to set up these equations so that we can solve them. So let's look at this Fx first. All right, so I know 0 equals what the sum of the Fx forces are going to be F1x plus F2x plus F3x. And if I actually write down what those are, my F1x is going to be this 42 kips here in the negative x direction. And it is entirely in the negative x direction. So it is going to be negative 42 plus my x component of F2 is going to be F2 times cosine 28, right? So I'm just working off of this triangle here, just like we did with resultant forces. It'll be F2 times cosine of 28. And then if I look at my F3, I've got a ratio triangle. So I could go and back solve and find the angle, but this ratio triangle tells me everything I need to know. I know it's a special triangle. It is a 3, 4, 5 triangle, right? So I can just use the ratio relationship of these instead of using sine or cosine with an angle. So my ratio relationship here is the x component over the total, right? So that's this 3 is the x component over the total is 5. So I can write it as plus f3 times 3/5. This is my full equilibrium equation. I can rearrange it some if I want right now, but I can see that I have two unknowns in it. So I need a second equation in order to actually solve for what those unknowns are. So I'm going to go ahead and set up my y summation equation. So that's going to be 0 is, instead of writing it out again, let's write it like this. That 0 is f1y plus f2y plus f3y, right? Same application, same concept, now just with all the y directions. So our f, I'll go ahead and do it in a different color. Our f1 has no y components. So f1y is going to be 0. And then I'll look at my f2 here. My f2, I'm looking for this y component here. It is going to be f2 times the sine of 28. So plus f2 sine 28. And then finally, I'll find my f3 component. And again, I'm just going to use the ratio relationship. So it's the y component of it over the y component of it over the total. That gives me the ratio. But notice this is negative, right? Our y is going down. And this is why it's so important to set the coordinate system. So that way we can see which way is the positive x direction and which way is the positive y direction. I had just assumed a normal coordinate system of a positive x being to the right and a positive y being up. But it's very important to set your coordinate system so that all of your signs come out correctly on this. So I have a negative minus f3 times 4/5. And this is my y relationship. And the really great thing about this one is that I can start moving things over. So if I add f3 to each side, right, add f3 times 4/5 to each side, I get that f2 sine 28 equals f3 times 4/5. And from there, I can do the arithmetic, right? That's all it is, just doing the arithmetic. Divide by sine 28, and I get this relationship, that f2 is 1.7 times f3. And so this is now just basic algebra that most of us probably learned in high school, that we're going to be just solving the system of equations, right? We're going to take this guy, plug him in to this equation up here, and now I have a single variable for that equation, and I should be able to solve and get what f3 is equal to. I'm going to go ahead, I'm going to erase all of this. Do I want to erase all of this middle? Maybe I don't. Okay, I ended up erasing everything that we aren't interested in. So all we're interested in is substituting this f2 relationship, right? f2 equals 1.7 f3 into this equation we found earlier. So what I'm going to do, I'm going to go ahead and move the 42 over here. So I'm going to say 42 equals, our f2 is 1.7 times f3. So 1.7 f3 times cosine 28 plus f3 times 3/5. So from now from this point, it's just your basic algebra, your basic combining these two terms together, right, equals 42. So what we have here is, if I combine these terms together, I get 2.1 f3 equals 42, and just dividing that out gives me f3 is 20 kips. So that's it. That's all I need to do is I need to find my magnitude of F2 and F3. I found F3, right? Just my basic algebra. I found F3. I substitute this 20 back into this equation here. And if I do 1.7 times 20, I'm going to get F2 is 34 kips. That's my final answer. That's all I need to do. It's just going to be a lot of setting up and solving these systems of equations. So that's why it's so important to have these free body diagrams correct. So that way you can see exactly what goes into these summation equations. It's going to be really, really important as you're setting up these systems of equations because it's so easy to make a sign error or to make an angle error, a sine and cosine, not just a sign error in both senses, a negative sign versus positive sign, a sine versus cosine. It's really, really easy to make those mistakes, and then you end up with an entirely wrong answer just because you had a negative sign instead of a positive, or vice versa. So we're going to go through a few more examples of setting these up, seeing how they work. But this is really it. It's really just getting the setup correct is the most crucial step. And then the rest of it is basic math. I mean, it's basic algebra that you all know and can do really well. There's no question in my mind about whether you can do the algebra. It's getting everything set up correctly. That's really the critical part of this. So let's look at another example, a slightly more complicated one, where now we're going to be setting up multiple free body diagrams and using multiple systems of equations to try to figure out our answer. Okay, so let's take a look at this example where I have a system on the left side, and what they want is they say the system is in equilibrium and we need to find W, find the weight. This guy right here, this weight that's hanging off point C. So what I need to do is I need to find my free body diagrams. Right, I'm going to go ahead and assume a normal, just positive y, positive x, positive y is up, and positive x is to the right. A standard coordinate system for this. And then I need to set up my free body diagram. So the first one I'm going to do is I'm going to go ahead and set up one at point C. At that knot at point C where I have 3 different cables coming off of it. So I'm going to have 3 different forces there. So I have at point C here, I have W, the force of W coming down off point C. That's what we're looking for. Then I have this force coming up by this 5, 12, 13 triangle. Again, another special triangle that we're seeing. This 5, 12, 13 triangle, I have this force coming up that is force CD. I'll call it just because it goes from C to D. And then I have this force coming down at a 3, 4, 5 ratio triangle. This force BC. I do sometimes put these relationships on the free body diagram itself. It might be a little bit messy if I do it here, but I do often put them on the free body diagram just so I can refer back to it, make it an easy reference for myself. So I don't have to refer back to the big drawing. This is a 5, a 3, 4 triangle, 5, 12 triangle, and this is my free body diagram. You don't have to put those pink ratio relationships as I have them there. It just helps me personally see. It's up to you. All right, so we're going to go ahead and we're going to set up the equilibrium equations. Apply the equilibrium equations, right? That's step 3. Apply the equilibrium equations to this free body diagram. So I'll go ahead and say the sum of forces in the x direction is 0. And so my BC, my FBC is in the negative x direction. So I'm going to look at that one first. Negative FBC times its ratio in the x direction, 3/5. Right? 3/5 in the negative x direction. plus my FCD is in the positive x direction, and it has a ratio relationship of 5/13. This is a special triangle, 5, 12, 13. 5/13 times FCD. And then of course W has no y component, has no x components. It is all y, right? So from this I can actually go ahead and get my relationship between the two. So I can say FBC equals, right, this way, 3/5 FBC equals 5/13 FCD. And if I multiply this side by my 5/3 to cancel this out, I will get FBC equals my 25/39 FCD. I'm going to go ahead and just highlight him in blue so I don't lose him, because I'm going to need to come back to this. Right, so I have, now I'll do my summation in the y direction. Right, so Fy equals 0, and here I'm going to have, we said my weight was entirely in the y direction, is in the negative y direction, negative W, minus, because FBC is also in the negative y direction, FBC times its ratio relationship, which is 4/5. Right, 4 is the y component of that 3, 4, 5 triangle, plus FCD. The y component of that, of FCD, is the 12 portion, 12/13 from the 5, 12, 13 triangle. So now, as we can see, I actually have 3 unknowns here and not enough equations to solve them from this single point alone. So what I'm going to need to do is move to a different point, do another free body diagram, and solve from there. So what I'll do is I will keep these 2 relationships, but I'm going to move down now to point B. And I'm going to draw a free body diagram around point B and see if that will give me the relationships that I need in order to actually solve these 2 equations. So let's draw my point B in blue here. And I have force FBC. Now remember, the forces always go in the opposite directions, right? So from this point C, FBC was going out, down in the negative x and negative y, and now you're seeing the equal and opposite. You're seeing the same force now in the completely opposite direction coming through the cable. This is standard. This is how we always denote this, which we'll talk more about later, but right now it's important to understand the concept that we're always pointing these forces away from the point we're looking at. So I have FBC, I have down by this force of 1,000 newtons. I have this weight of 1,000 newtons that's already here. And then I have straight to the left. I'm going to call this FA. Just because it's going in the A direction, I'm just going to call it FA. Entirely in the negative x direction. So I can set up these equilibrium equations as well. Let me move these up. I don't need this top one anymore. I just need these guys. So I'll move these up here. And we'll set up our equilibrium equations here. So our sum of fx for this one, always 0, is going to be FA is entirely in the negative x direction. So it'll be negative FA, right? Just FA, no components. Plus FBC and the x component of FBC, right? Just the x component of FBC in the positive x direction. which FBC is related by the 3, 4, 5 triangle. So it's going to be times 3/5. Right, so I could rewrite that as FA equals 3/5 FBC. Now let me look at my y components here. Fy, sum of all Fy components equals 0. Fa has no y components to it, but I do have this negative 1,000, this negative 1,000 newtons. Plus, for FBC, I have the y component of FBC is FBC times 4/5. And it is positive since it's in the positive y direction. So actually, I did not need this equation at all. We didn't need to solve for this because as we can see, we can now solve this equation right here to find out what FBC is, right? So if I subtract, or if I add 1,000 to each side, I get 4/5 FBC equals 1,000. And so if I multiply that over, I get what? 5,000 over 4 is FBC is 2150 newtons. So now that I have that, I have enough of a chunk that I can plug this guy into this equation up here, solve for FCD, and then plug both of those into this equation here and this equation here and find what W is. So let's go ahead and follow through. Let's go ahead and do that. Let's remember this FBC is 1250. So FBC is 1250. I'm going to put that right here. It's 1250. Right here it's 1250. Okay. So 1250 that I'm going to multiply 39 over 25. I'm going to multiply that over. So that's 1250 times 39 over 25. Sorry, I didn't write this down. I punch it in my calculator real quick. I get FCD is 1950, which I will then plug into here. So I get W, moving this W over here, W equals FCD times 12/13 minus FBC times 4/5. All I did was rearrange this equation here just into something that is a little easier for me to work with. And now I'm going to plug in the values that I know. FCD we said was 1950 times 12/13. And FBC we said was 1250 times 4/5. So 1950 times 12 over 13 is going to give 1800. And then 1250 times 4/5 is going to give 1000. So 1800 minus 1000, W equals 800 newtons. This is the weight required to put everything into equilibrium. Now, before we do a couple more examples, I want to bring up some special systems that we end up seeing a lot in statics. And the first one that we end up seeing a lot is springs. Now, if you haven't taken physics, you may not be familiar with this, but our spring force, when we're looking at a spring and some force acting on the spring, spring force is represented by Ks, where K is a spring constant. This is usually given to you. Sometimes you have to solve for it, but the spring constant, which always has units of newtons per meter or pounds per inch or foot. It could be either pounds per inch, I would say is more common, or pounds per foot. This is what you'll see the spring constant. And then this S value here represents displacement. And what I mean by that is when you have a spring that is unstretched, so the spring is just sitting here, no force applied, it has an initial length that I'm going to call L naught, L with a subscript of 0. We call this subscript 0 naught, L naught. So this L naught is the initial length before it's subjected to a force that stretches out the spring. And then when I do stretch out this spring and subject it to a force, now it goes this additional length, S. This is how much the length changed from L naught to its final length, which we often just call L. Its final length of L minus L naught is what represents S, the displacement. How far out that spring stretched. So this is what our S is, and then our K is usually given a spring constant. And that's how we find force in a spring. So we'll see that in some of our problems, and in a free body diagram, we still represent it as just a force, but it's a spring force. So we know instead of using F equals ma, what we'll want to use is F equals Ks. And then one more kind of special situation that we do come across quite a bit are pulleys and cables. Now, anytime we have a pulley, which is going to look something like this, it'll be a circle, a large circle, usually with 2 ropes coming off of it. This is our pulley. Anytime you see a pulley, we make a few assumptions. We usually assume the pulley is frictionless. So we're not going to take into account any friction forces for the pulley. And for the cables themselves, the ropes that come off of this pulley system, we always assume that they are in tension. And only tension. They're never being compressed, they're never being squeezed. We always assume that the forces are coming out in tension, which we often label the tension force as a capital T. So those forces are coming out in tension. We also assume that the cables don't weigh anything, so they're not contributing any mass, anything like that. We ignore the weight of them, and we assume that they don't stretch. They don't, not like a bungee cord. How a bungee cord stretches out when you pull it, we assume that these cords do not stretch, right? They get pulled tight, and that's it. They don't stretch at all. There's no give. There's no weight, and they don't stretch. But the most important thing that we need to recognize about a pulley system is that this tension through the cables that go around the pulley are the same. These 2 values are always going to be the same, no matter what angle these guys come out at, right? So it doesn't matter. They could be at any angle. The tension is always going to be the same throughout the rope, because this is one cohesive rope that stretches over the pulley. And there's no friction to change the force. So the force that is coming out from one end of the rope is going straight through to the other end of the rope. So we'll look at a spring example and then a pulley example to really kind of see how these things work. So in this example, we're going to be looking at a spring. And at first, it doesn't look like we're given much information at all, right? All it wants us to do is find the force in cables BC and BD, but we're not actually given any forces to begin with. So what we are given is the initial length of the spring the K value of the spring, and then this value here is the stretched out value of the spring. So from there, we know that to get our force to do anything, before we can even really start the problem, is we need a force to work with. So our force we can get from Ks, where, if you recall, our S is our stretched length minus our initial length, which in this case, our stretched length is 500 millimeters, minus the initial length of 200 millimeters. So that S value is 300 millimeters. Or, this is important, remember to convert your units, because we can see that our K value is in newtons per meter. So I can't multiply 300 millimeters by something that has units of newtons per meter. My units aren't going to match, and my answer is not going to make any sense. So I'm going to go ahead and convert this to meters by dividing by 1,000 and get 0.3 meters. So now all of my units are correct, and I can plug this guy in over here, and I get the force is 800 newtons per meter times 0.3 meters. So when I plug that into my calculator, I get a force of 240 newtons. Now that I have a force to work with, now that I have a starting point, I can go through the equilibrium steps, right? So setting a coordinate system, I'm just going to go ahead and assume the regular positive x and y directions, the standard x and y directions. And now that I have that, I can draw my free body diagram to solve for what the forces are in cables BC and BD. So let's go ahead and set that up. Let's get our free body diagram set up. My force is that 240. So that's going to be the first thing that I write down before I forget. So I'm doing a free body diagram around point B, because that is what all three of these forces are touching, right? Here I have the spring force, which we just said was 240 newtons. Then I have cable BC, I call it FBC, and cable FBD. Now again, it isn't giving me any angles, but instead is giving me distances that will allow me to determine the ratio relationships. So here I see for cable BD, I have 400 millimeters and 300 millimeters. So if you'll recognize, these distances are telling me that I have a 3-4-5 triangle ratio relationship, right? So I have this 3 is the y direction, 4 is the x direction. I have a 3-4-5 ratio triangle on. And if I look at my upper portion, my 400 is still here in my x direction. But now I have a 400 here in my y direction, which is telling me, since both sides are the same length, that I'm dealing with a 1 square root 2 triangle, a 45-degree triangle, which you can feel free to write in either way. In fact, let's go ahead and just write it in as instead of a ratio relationship, we'll just write it in as a 45-degree angle. So this is 45 degrees. So that's my complete full body diagram. From here, I'll go ahead and apply the equilibrium equations. So I have some in the y direction. I'll start with the y direction this time, just for fun. In the positive y direction, I have FBC. I have FBC times sine of 45. FBC sine 45. And then I have FBD also has a y component. Our 240 has no y component whatsoever. But my FBD does in the negative y direction, right? Minus FBD. And then it has a ratio triangle where the y component is 3 over the total of 5. So for this, I can easily now go and back solve, right? I can set up this relationship, solve for one of these variables. So I'll go ahead and say FBC equals, if I plug that in my calculator, I get 0.8485 FBD. And again, that's just the algebra rearranging this equation here. And then all I do is I do it again for my x directions. Sum of forces in the x direction is 0. We have our 240 is entirely in the negative x direction. Plus, each of these two forces are in the positive x direction, so they'll both be added. Plus cosine 45 times FBC. FBC cosine 45. Plus our x direction is the 4/5 ratio. 4/5 FBD. But of course, I can already go ahead, since I did this y1 in the first place, I can substitute this in right here. And I can just do the arithmetic to solve what FBD is. So if I plug this in and rearrange the equation, right, all I'm doing is just rearranging the equation, I can find that my FBD equals around 171 newtons. I imagine you all can mostly do this algebra and arithmetic on your own. Try to work it out yourselves if you're confused on how I got from these two equations to this answer of 171. You might want to go back and find some videos on how to solve systems of equations and the best way to do that. Do a refresher on your algebra, but this is the correct derivation that you get when you go through the algebra for this. So I get my FBD is 171, and if I plug this guy into this equation, then I find my force in the BC cable is going to be around 145.5 newtons. And that's all it asked me for. It asked me to find these two forces in the two cables. Notice that these are two separate cables, so they have two separate forces. But again, as we're going to see in the next pulley problem, sometimes the cord is entirely the same and the tension through that cord is the same. Let's take a look at an example like that. In this example, I'm going to try to find the mass of cylinder A in this system that has a pulley in it. This pulley is this circular part right here. And so what I'm going to do is I'm going to draw a free body diagram. Well, my coordinate system. I'm going to assume the regular coordinate system. And I'm going to draw a free body diagram for this point right here. I always want to start near my unknown, include my unknown force in my first free body diagram to see if I can solve it from just with what I know. So I'll go ahead and draw this free body diagram. I have the weight from cylinder A, which I'm going to just call weight for now. I have the force, which I'm going to call T, the force that is coming through the tension of the cable that goes over the pulley. I'm going to call that T. And then I have this force, I'm just going to call it F, that goes straight into the wall. Okay, so now I have my free body diagram. I know my coordinate system, and now we need to find out what the mass of A is. But we have this pulley in there. And the magical thing about a pulley is that the tension through the pulley, this tension that is coming off right here, this tension is going to be exactly the same as the tension coming down through the pulley, right? So what that's telling us is that our tension is actually going to be equal to the force that this side of the pulley is experiencing. And what that force is going to be F equals MA. In this case, 40 kilograms times 9.81 meters per second squared. And so that is going to give us I did not write it down. That is going to give us 9.81 times, punching this in my calculator, 40 is 392 newtons. So that is my T. This is T. So now I know T, and I don't need to care about my X component forces. I only need to do an equilibrium here in the Y direction, because what I'm looking for is this W, and he's only in the Y direction. So since I know my T, this is 30 degrees. Fy equals 0, sum of forces in the Y direction equals 0 is going to be T times sine of 30 minus W. And so what I'm going to end up with is W equals 392 sine of 30. So when I punch that into my calculator, times sine 30, I get weight is 196 newtons. But they asked for the mass of cylinder A. So I'm going to go ahead and divide out 9.81 meters per second squared. 9.81, and what I get is 20. I get the mass of cylinder A is 20 kilograms. Now, in fairness, this free body diagram would have also worked as entirely masses, is if I just would have left these instead of as force vectors. If I just left them as masses, I left them as mass values, my math still would have worked out the same way. I just left them as force vectors because that's what we're primarily going to be seeing them as. So we'll do some more examples in the next video, and we'll also introduce how you approach this in 3D as well. But for now, just remember the 4 basic steps of how we go about solving these problems in equilibrium, which is setting your coordinate system, making a free body diagram, and then applying those equilibrium equations, which in 2D is going to be the sum of forces in the X direction equals 0, and the sum of forces in the Y direction equals 0. And you repeat that as many times as you need to until you can solve for all of your unknowns.